Hello there everyone. So today I would like to discuss about the last application of differential calculus, which is optimization. We have already been doing that for quite a while now, so it shouldn't be anything new. So simply when we're asked to optimize a function, we may use usually three different methods. So we may use our calculator. So if we're given a function, for example, f of x equals x to the power something, blah, 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 you may just put that function in your calculator, and that's going to give you maximum and minimum points. They might be local, they might be absolute. So let's say, for example, if my function is just defined between those 2 points, this is, I don't know, xa, and this is xb. So my function is not valid outside of those boundaries. So if we notice, if we plot, for example, this function, if we had the equation of it, we would find one maximum here, and we would find a minimum here, and we can use a calculator for that. So let's just assume that we're given a function given by x to the power 3 minus x squared plus 5. Now if you grab your calculator and you go to graph, so it's option 5 here, you may put in your function. So yeah, this is slightly different. It's 2. Good, so both equations are now the same. X to the power 3 minus 2x squared plus 5. So if we draw this function, that's the graph that we get. That's what we expect from a cubic function. Now if we want to find the top, the maximum here, that's the local maximum, and the local minimum here, we could just use graphical solver. So min, it gives us a local min, and graphical solver max, it gives us the local max. So when x is 0, y will be 5, and that's a maximum, local maximum. And when x is this, right, which is an ugly number, y will be a min, and that's the height of our function at that point. Now calculators help us a lot, however we might not always be able to use them. So the second method for optimization, for finding local minimum or maximum, or absolute minimum or maximum, is using the equation for the vertex. So there's a formula, x equals negative b over 2a, and that gives you the vertex of a quadratic, of a parabola. So that's another way of finding a maximum or minimum of a function. So in this case, if your function is something like x squared plus 2x minus 3, what you have to do is negative b over 2a. Now this function, since a is positive, we know that it's concave upwards, right? Because a here is 1, so it's greater than 0, it's positive, so it's concave upwards. And if we do negative b over 2a, so x of the vertex, negative b here, that's take away 2, over 2a, that's 2, so that's minus 1. So this would be the position of our x, and we may just get that x back and find the height. So by using this formula, it helps you a lot. Now this formula is also quite easy to deduce. Just assume that you have a parabola, ax squared plus bx plus c, and get the derivative. So if you get the derivative of this, it's going to be 2ax plus b, and since it's a max or min, that should be 0. So if you rearrange this, you will have exactly minus b over 2a. Now the third method, that's quite expected, it's using calculus. So by using calculus, we can also find maximums and minimums. And let's take a better look at this last option now. So just like the function that I showed you before, if you had a function like this, right? It's not going all the way to infinity, neither positive or negative. However, just by looking at this graph, we would be able to declare that there's a maximum here and there is a minimum here. But what does it mean according to calculus? What does that information mean? Well, if you have a maximum or a minimum, your derivative of y according to x will have to be 0. So that's a stationary point, remember? But in this case, it was growing and then it becomes less, or it was going down and then it starts growing. So to analyze if it's a max or min, if you cannot see the function, you will have to analyze how is the surrounding of this function. So for example, if I take any derivatives, so let's take this point a here. If I take derivatives to the left of a, my derivatives will be positive. If I take derivatives to the right of a, my derivatives will be negative. So if we plot a sign diagram for this case, we would then have, let's say, point A here in the middle, and it should be lowercase because it's a point. So our gradient is increasing before and decreasing after. This is your gradient. Okay, I'm only caring about this particular point now. So it's growing before and it's going down after. So there's only one way for this to happen. It must mean that it's a concavity downwards here. Therefore, this is a maximum. And well, obviously, if you do the same thing, but it's the other way around, if it's negative before and positive afterwards, then it's quite the opposite. If it's negative before, it means it's going down. So it was going down here, and then when it went through a, derivative is 0 and then becomes positive. So this is a min. And this is also sign diagram for the derivative. Now the sign diagrams are not 100% necessary here because you have another way of checking for local minimum or maximum. There's another way basically for you to find out if the curvature is downwards or upwards, and that's by taking the second derivative. So if you take the second derivative of a curve which is concave downwards, your second derivative will be negative. If you take the second derivative of some parabola which is concave upwards, or any segment which is concave upwards, that will mean that the second derivative will be greater than 0. And therefore, if your derivative is 0 and your second derivative is less than 0, then it's a maximum point. If your derivative is 0 and your second derivative is larger than 0, then it's a minimum point. So let's have fun with a very simple example here. So this actually happened to me while I was in grad school. And basically, let's assume that there's a container. I had to do it practical, and I had to fill a container with water. The only information that I knew that I needed was that the volume was constant, and I'm going to assume that it's just 1 cubic meter, just to make things a bit easier. Also, I had the limitation that my base had to be square. So if this is x, this will also be x, and the height is any. So my question was, how can I build this? This is like a box. So there's nothing on top here. It's a container for water, for fluids. And so in such a problem, I'm going to be asked, how can I make the area of those here the smallest possible? So I'm trying to build this box, and I want to use the least material possible, that's all. So I'm trying to make the areas here small, the smallest possible. So the volume is constant. However, I need to make those areas the smallest possible. And obviously the areas are going to change with x and y. And how? Well, if I open this up, I will have one area here at the bottom, which will be x squared, right? This bottom here is x squared. Now each of the sides will produce an area of xy. Since there are four of them, 4xy. Now this is the formula for my area, and I've got two unknowns. And it might look like we have two unknowns and only one equation, but that's not the case because the volume is known and we should be able to calculate the volume as well. So the volume is given by the product of the area of the base by the height. So x squared y, and that's equal to 1. Now since that is equal to 1, I could just write y in terms of x, and we would then have that y is 1 over x squared, or simply 1 x to the power negative 2. So this area here is a parabola. We can see that it's a parabola upwards. So we want to find the minimum point for this function, so that the area is going to change with x and y, and there will be a certain point where it's going to be minimum. So to find the minimum, we will have to differentiate our area in terms of its, well, in this case, this length x. So if I take the derivative of function a, I will have 2x plus, now y here, I will have to replace and put everything in terms of x, right? So let me rewrite this equation before we move forward. So if everything was in terms of y, this would be x squared plus 4x over x squared. So our area only in terms of x is x squared plus 4x to the negative 1. This is our formula for the area. So when we take the derivative of the second portion here, this sign will flip, and that x will become negative, the exponent will become negative 2. And since this is a minimum, or well, since we're optimizing this function, the derivative will be 0. So what does that mean? Well, that means that 2x will be equal to 4 over x squared. That's the follow-up from this, moving that to the other side, right? And here we'll arrive at x to the power 3 is 2, which means x is approximately 1.26 meters. Now, what if you didn't know if this function was a maximum or a minimum, and you want to make sure that this is going to provide you a local or absolute minimum? So what you may do is take the second derivative. Since you have the equation, it's fairly easy to do so. So taking the second derivative of this according to x, this first term, well, x will vanish, now it's only 2, it's the constant now, and this will again, this exponent will drop, so negative 2 times negative 4, that's positive 8x, and negative 2 will become negative 3 now. Now what happens when we apply this point? Because what we need to find is, okay, this is our second derivative. What is the second derivative at that point? 1.26 meters. So that's 2 plus 8 times 1.26 to the power of negative 3. And that gives 6. That's 6. So this is positive. What can we deduce from that? So that means concavity is upwards. Well, and obviously, one last thing that it could be asked is, okay, you've done all of that, what is y? Because to actually build this, you not only need to know x, but you also need to know the height. So we can just get back to one of the first relations that we have found. So y is 1 over x squared. So we can just put 1.26 here, and then we would find y to be about 0.63 meters. And if we multiply this by this squared, we should find 1, which matches our original volume.